Okay, I think it's a very good time to start, I think, UN's talk. So shall we start?
Yes.
On time.
So I think I can share my screen.
It's exactly on time.
Yes.
10:09.
Yes.
Okay, good.
So I think first maybe I could you see it?
Okay.
Okay. So
Here.
So I think firstly I would like to thank Professor Huang's opening, and especially I would like to thank Dr. Yoshiki Toba and Professor Boyo Kachukade to accept our invitation. And I would like also to thank Chao Gui and Li Fang's help for this symposium. And I would like also to thank Katria to hold this meeting together. So today I would like to talk about galaxies with large surveys. So after the Big Bang, dark matter halos are formed out of the initial density perturbations. Then galaxies assemble layer mass through accretion and emergence along the cosmic webs. So if we study the evolution of galaxies, we are able to know the evolution of our universe. So today we know that at around Reich 2, so it's about 10 giga years ago, there are a huge population of galaxies. So and today we have enough technology to detect and observe these galaxies. If we use a telescope such as Hubble Space Telescope to observe the sky, we are able to study the evolution of galaxies. So, however, the evolution of galaxies is not observable. We are not able to observe a galaxy from its birth to death. But if we have a huge population of galaxies, we are able to see their evolution. So at different epochs, like from the very early time to now, if we can use a ground-based or a space telescope to observe the sky, to go very ancient times, then if we have a huge enough database, we are able to know the galaxies at different epochs and to tell a story about their evolution. So this is a deepest image from Hubble. This is the Hubble Ultra Deep Field. So there are tens of thousands galaxies in this deep field. And this year, in astronomy, we start to have James Webb Space Telescope, JWST. So therefore, we are able to look into deeper skies. So for example, in this kind of deep image, there are many galaxies. Some of them are rounder and some of them are flatter, and some of them are bluer and some of them are redder. So they all have different physical properties. So one of the most important questions in galaxy evolution is that how do star forming galaxies evolve to quiescent galaxies? So star-forming galaxies are young galaxies with structures and active star formation, and they usually look bluer. So if they stop their star formation, they become quiescent galaxies. So the quiescent galaxy, also called as passive galaxies, they have smooth structures and they have little star formation. They have more old stars and they look redder. even though we know we have these two groups of galaxies, we still don't know how do star-forming galaxies evolve to quiescent galaxies. So this is an important question. We try to study galaxy properties. So for example, if we plot the stellar mass to star formation rate plot here, we can see the star-forming galaxies are in the star-forming sequence here, and the quiescent galaxy is in the right lower part. So they are separate. So we are curious about how this mechanism works. So one thing we can explore is layer size evolution. So it has been studied that the sizes in the past is very different from today, even if they have very similar physical properties. So at the same stellar mass being, so star-forming galaxies is about 2 times smaller in the past, around 10 giga-years ago. So for quiescent galaxies, the difference is much larger. So it's about 5 times smaller in the past. So it means today our galaxies are much larger. And in the past, the galaxies are smaller, which means they are more compact. Another thing we can also explore if we have deep images. If we study the population of galaxies, and we know that at around ratio 2, most galaxies are much flatter than today's galaxies. So this is a result for quiescent galaxies, and we saw that the majority of massive quiescent galaxies ratio 1 are flat and more disk-like. So another thing we can study is to see their visual classification, how they look like by layer morphology. So one thing is highly discussed when we talk about galaxy evolution is that galaxy have mergers, and it can destroy the whole structure and make the galaxy different. So if we want to study layer morphology, we have to check the images one by one. So by visual classification, we are able to know whether galaxies are different. So with the above results, we are able to answer how do galaxies form and evolve over cosmic time. So because in the past, galaxies are much smaller and more flatter and compact, it is possible that quiescent galaxies are formed disk-like and become larger and rounder through galaxy mergers. So, and because today we have, for example, like JWST or other telescope, ALMA or some observations, we are able to study more about layer structure, and even for even older galaxies. So then another topic I would like to talk is AGNs. AGNs is highly discussed when we talk about galaxy evolution. So in theory, it is possible that AGN plays a role when star-forming galaxies evolve to quiescent galaxies. So it has been highly discussed that supermassive black hole AGNs, which is called active galactic nucleus, and the galaxies has a co-evolution. So even though they are in very different scales, which means black hole is about 1,000 times smaller than AGNs, and AGNs are about 1,000 times smaller than galaxies. Still, because of the mechanism of AGNs are very strong, it's possible that they have a strong connection. So, so this is a AGN model. So in the middle of an AGN, we can see a supermassive black hole, and it follows an accretion disk, the blue part here. And outside this disk, we may have some torus. And on the two sides of an AGN, it's possible to have jets and outflows. So therefore, if we use multi-wavelength observation to trace AGNs, we can see their different structures. So this kind of object is firstly identified as different names because they have very strong emissions at different wavelengths, like in X-ray, far-infrared, visible light, or in the infrared part. So Toba-san's talk will also talk more about AGNs, especially for dust obscure AGNs. So we can hear more stories about AGNs with multi-wavelength observation from Yoshiki's talk. So in here, I would like to introduce infrared select AGNs. So this is a work we have done before. So for infrared select AGNs, we are able to use spectral energy distribution SEDs to separate the AGN structures. So with the orange curves in the SED in the right part, you can see we separate the layer SEDs to star-forming galaxies and the AGN, the torus emission parts. Therefore, we are able to get their physical properties. So we did this SED fitting for the whole cosmos field, for a deep field. Then we are able to tell whether AGNs are different from other normal galaxies. As a result, we find that for our obscure infrared AGNs, they are about the same as the star-forming galaxies. So, which means they are on the star-forming sequence, as you can see, as in the left side at low redshift. So another thing we can try to explore is layer size and morphology. So we also did another work to check layer physical size. So as a result, we find that for galaxies with AGNs, layer size are more compact at the same redshift and stellar mass beams. So this is a result from Hubble Space Telescope, which means they are near-infrared observations. So it traced the stellar population of the host galaxies of AGNs. So we also extend this work with AMA observations, and we found that with the AMA observation, the AGN host galaxies from our select sample are also more compact than non-AGN star-forming galaxies. This means no matter in the optical part or in the radial part, we all see this more compact trend. So it can be explained by that both the stellar and the dust structure of an AGN host galaxy are more than normal galaxies. So to study this kind of questions, we are able to answer how do black hole affect galaxy evolution. So one possible explanation is that when star-forming galaxies become quiescent galaxies, agents are triggered by this process, or even agent can play a role when star-forming galaxies become quiescent galaxies. So therefore, the structure of agent-host galaxy are different from galaxy without an agent. They are more compact. Then, if we want to study more about this kind of subject, one thing we can do is to have more sample. So recently, we start to do some machine learning project. So the first project is to identify agents by machine learning method. So we some label data in a cosmos field in the left upper part, as you can see. We already identify agents and non-agents in a deep region. So before we need lots of information, like more than 20 bands to distinguish agents or not agents. However, if we can create a machine learning model, we are able to apply this to new data, such as HSC and WISE data in a wider field. So this means we don't need to have deep images or multi-wavelength observations to confirm whether they are agents. So in our work, we use different Python packages and to predict agents and non-agents for data which is not classified before. So the data we use for the label agents is in a cosmos field. So it's about 2 square degree field in our sky, and it's covered by the HSC field, as you can see in the lower part. And it's also covered by the WISE data. So we are able to use our model to apply the smaller field to larger fields to know whether galaxies are hosted by an agent or not. So the input data are the SHC and the WISE data. So from previous studies, we already identify agents in a cosmos field. So we have about 30,000 galaxies. And some of them are identified by X-ray agents. Some of them are identified by infrared agents and radio agents. So we separate this data to 2 sets of training sample and 1 set of testing sample. And because agents are about 10th of the whole galaxy sample, we also use oversampling technique to consider the imbalance between the data. So to test the performance, there are several scores we can check. So for example, we would like to know how many agent source which is classified as an agent. It calls the true positive rate. So in the best case, the true positive rate should be close to 1. So which means all the agent sources are classified as an agent. And we also want to have a true negative, a high true negative rate, which means a non-agent source which is classified as a non-agent. And here we also need a very low false positive and false negative rate. If you are familiar with, sorry.
Sorry, I have a question.
Yes, please.
So, in the previous slide,
yes.
So actually, there are many definitions of
Yes.
AGNs, I think. Say
Yes.
radio AGN. Could you go back one more slide?
This one?
Page 25. Yes, it is. Infrared AGNs and then X-ray AGNs. So probably they have different definition or different
Yes.
criteria to
Yes.
set AGNs. But in this one, so basically, if you sample satisfy one of them, say either radio or IR or X-ray.
Yes.
If you sample satisfy one of them, then you say it's AGN.
Yes, normally if it's satisfied with one observation, we say it's AGN.
Yeah.
But usually in observation, we will still call X-ray selected agents or infrared selected agent or radio selected agents.
I said, thank you very much. And then my point is, say, for example, if I look at the X-ray AGN,
yes,
the circle is the circle, and then actually there are sources which is not classified as AGN by X-ray definition.
yes,
But for example, in terms of radio, they are AGNs.
yes.
So therefore, I was wondering how you define this true positive in next slide, true, sorry, false negative, true negative.
Okay.
So these are also related to, I think, how you define agents here.
So in fact, we did separately, which means, yeah, we did 3 catalogs and to see whether they are different kind of agents.
I see. You did the same thing for different agent definitions.
Yes. So like X-ray agent or non-X-ray agents, and also the same for other two kinds.
I see. I got it. Thank you very much.
Thank you for asking.
Thank you.
So basically, so maybe I make it full screen again. Yeah, sorry. So here, if we want to know the performance, we test their different scores. And if you are familiar with COVID news, you know that we want to have a very high true positive rate and high true negative rate and low false positive rate and low false negative rate. So in fact, in data science, it depends on which kind of topic you want to focus. And for each topic, we usually focus on different scores. So for example, we may also consider accuracy, which means the true positive sources plus true negative sources divided by the whole sample. And we may also care about the precision, which means in the whole selected sample, how much sources are classified as AGNs. And we also care about recall, which means in all the selected sample, how many are real AGNs. So depends on your topic, we usually care about different performance scores. So here, because if we want to identify agents, we want to select as much as possible, so we care about precision. But we don't want to have wrong sources, so we also care about the recall score. So here we have tried to consider all scope. So there are another scope which is called F1. This consider the harmonic mean of precision and recall, like you can see in the lower part here. And we use different classifier to classify agents, and the performance can be up to 0.65. If we use HG Boost, which is a very new classifier we have today. Another performance we can test is the ROC score, which is plot in here, which is the true positive rate to false positive rate. And because we want to have a high true positive rate and a low false positive rate, so the score, which means the area under this orange curve, should be close to 1. So this is a result for different kind of AGNs with our best classifier. So as you can see here, the ROC score is about 0.8, which means we can have a good classification for the sources. So if we test different classifiers, as you can see here, we can have also different numbers, and still HG Boost in this data can perform best. So in this work, we use HSC, the optical data, with WISE near-infrared data to identify AGN host galaxies. And from previous identified AGNs, we can have good F1 score and AURC score with the classifier we use. So another project we did recently is to identify galaxy modular stages. So in this work, we use manga data, which is IFU data belong to the SDSS survey. So in previous work by Pan et al. 2019, they visually classify galaxies, modular galaxies in different stages. So at stage 1, this means 2 galaxies are start to be merged. Then at stage 2, the 2 galaxies are start to collide with each other. And at stage 3, 2 galaxies are separated again. And at stage 4, the 2 galaxies are start to be merged together. So there are about 5,000 galaxies are classified at different stages, and in this sample, there are about 1,000 galaxies are in any modular stages, and here are the numbers we have for different stages. So, however, this work is very time consuming. People has to check the image one by one. So, therefore, it is worthy to use machine learning to classify the galaxy stage, the galaxy modular stages. So, in our work, we use very similar information as what people use for visual classification in the previous work. So the input data are a catalog which contains the projected separation and the line of sight velocity, dr and dv here. As you can see in the right part, we all have these numbers from manga survey. And we also use SDSS image GRI bands. As you can see here, we have 3 colors of optical images. And from manga data, we also use H-alpha velocity map, which is another images when people try to classify galaxy mergers. So at different stages, they look different. So we include all this data as an input before we do the machine learning test. So in this work, the most important score is the precision. So because we don't want to select a sample which are not galaxy mergers, it might be okay to miss some merger galaxies, but in our select sample, we want to have a very high precision. So which is also called purity in some cases. So as a result, we also test different classifiers, as you can see in the right plot. So for non-merger and the mergers, the precision can be up to 0.9. And if we want to classify galaxies in different merging stages, we call 5-phase classification from non-mergers, stage 1, stage 2, stage 3 to stage 4. The precision is up to 0.6. In order to increase the precision, we try different tests. So, for example, if we only focus on star-forming subsamples, the precision can be increased. And in data science, if we deal with images, it's also quite often to try to do pre-process. So because for an images from a merging galaxies, we know that even if we rotate the images, the physical properties are still the same. So therefore, we can rotate the images. Here I rotate one image by 90 degrees, and then we can increase the sample size. So we have to make sure whether this can be done in different cases. So for example, if we want to identify a car images, like a car on the street, we can flip the image, but we cannot make it upside down. But in astronomy, because the galaxy has no real orientations, so we can rotate different angles and also flip the image. So I also try to include more rotated image, but in the end we find maybe it's enough to have one original image and one rotated images. So as a result, if we increase the sample size by rotating the images, the precision can be up to 0.85. Especially with LGBM classifier, as you can see, the first classifier I show in the right plots. So these are 2 projects we are doing recently. In the first project, we are able to increase the sample size of agents by machine learning techniques. And for the second project, we can ask the machine to classify merging galaxies for us. Then in this case, we don't have to do visual classification for all the galaxies except the human times. Then ask the computer to do the work for us. And in both projects, we can have very good performance according to our purpose. Therefore, because today there are more and more data in astronomy, and I believe that with machine learning, this result can apply to our future all-sky surveys. So these are the things I want to show you today. Yeah. So yeah. So yeah.
Okay, thank you very much, Yuan. Thank you for a great talk. So now we have a time to have a questions. So do you have any questions or comments? Oh, please, one answer.
Okay. Okay, thank you for the wonderful talk. Because I'm not an expert in astrophysics field, so please excuse me to ask a stupid question.
No, there's no stupid question.
Okay, no, because I'm very interested in one sentence in your slide.
Yeah.
You say black holes affect galaxy evolution. So can you simply describe or explain how black hole affects the galaxy evolution or our future in the world? Because we know we are so attracted by the black holes, but also a little afraid of how black hole affects our future. So thank you. So please give us some briefly explanation for this effect.
So in fact, it's very difficult questions.
Sorry.
It's a good question. What I mean, it's a good question. So today, still people, astronomers try to find the connection between black hole and galaxies. And one thing we believe today is that in every galaxy, in the center of every galaxy, we have a supermassive black hole.
Yes.
So like recently, we observed a black hole inside M87, another galaxy, and our Milky Way. This news like in this recently.
Yes, I know.
So it's just be confirmed by observation that we know that inside every galaxies we have a supermassive black hole, and at least in a short term, it won't really affect our life because they are very far away.
Yes, it may be a long-term problem in the
Yes.
future, so maybe we can ignore the effect in our daily life.
And in fact, there are different types of black holes. So these are very massive black holes. So there are also small scale black holes, but they should be also not very close to us.
Okay.
And in observations, we try very hard to find the connections, but in fact today, until today, most of them are not very straightforward. So we just see if they have a massive black hole, they may have more star formation. So like they are proportional to each other. And another reason is that I talk about AGN model, and AGN model usually contains a black hole inside in the center as well. So this model is believed to be true, especially for people do theory, because if we don't have an AGN with a black hole, then the current observation is not consistent with theory. So they need to add agents in their model, to add a supermassive black hole in their model to have the same number of massive galaxies. So
Okay.
yeah.
So you mean in the present observation,
Yes.
we don't yet to find an enough massive black hole to affect our Milky galaxies.
We don't have straight evidence.
Oh, yes.
We just observed two massive black hole inside two galaxies, so it may be just a start.
Okay. Okay. Thank you for your
Thank you
answer.
for your question. It's a very good one.
Thank you very much for answering. So if I can add a little bit more, I'm not expert of AGNs, but I know that some people argue that if supermassive black hole can be extremely bright when gas accretes onto the black hole, then this brightness radiates a lot of cosmic rays. Then our Milky Way is not that active, so that the human beings can survive because we don't have many cosmic rays from for now.
Yeah.
But I think some people say if you have extreme activity of supermassive black hole in our Milky Way, then the many cosmic rays may come to the Earth, which may affect the lives on the Earth. Therefore, but this time scale is totally different from our lifetime. Therefore, for now it's okay, but for far future,
Yes.
it may affect. That's my understanding.
Thank you for your prediction. It led me my field safe.
Thank you.
Okay, thank you.
Okay.
Thank
So actually, it's time, but still we have a little bit of time to have more questions. Is there any question? Oh yes, please go ahead.
So can you hear me?
Yes.
Thank you for your talk. And in the slide about 13, so is that mean Adrian is one of the reasons that make a star-forming galaxy transform to a quiescent galaxy? Is that true?
It's a highly discussed scenario when people do simulation, because for massive galaxies in observation, we don't see so much massive galaxies in observation, but in theory, we predict much more massive galaxies. So AGN, it's why people start to think AGN can be a reason to stop star formation. So therefore, especially in theory, the outflow or jets from an AGN is possible to have positive feedback and then start the star formation, then make star-forming galaxies become quiescent galaxies. But still, I have to say it's a very useful scenario if people want to explain the inconsistent between observation and theory. So, but still, we cannot say it's the truth. It's just one possibility.
Okay, so which time will the Adrian will appear? It will in the original star-forming galaxy, in the middle of them, or in the end of star-forming galaxy, Adrian will appear.
So it's also not a very that's also not a clear answer to this question. And as far as I know, people try to find Adrian in the middle of process. And there are some findings says Adrian tends to be have larger population in star-forming galaxy groups. But still, because we have selection bias, it depends on what kind of Adrian sample you select. It can be different. But what you say in the middle of the process is one possibility.
Okay, thank you.
Thank you.
Thank you very much. Oh, okay. Please go ahead.
有声音吗？
It's good.
I want to ask what causes the jet of AGN?
What caused the jet of an AGN?
Uh.
So as you can see, the black hole is here. Yes, and if we have an accretion, then there's some materials falls into the black hole. So it's possible they have very strong strong activities. Then jets are emit from the center of a black hole. So it's one possibility.
Okay.
Thank you.
Okay, so please go ahead. Sorry, I can't read the Chinese name.
叶启
And can you hear me?
Yes.
Okay. I'm not sure what the page is. Maybe it's in the 27 or 28.
7.
Maybe in the 30. I'm not sure, but that's in
What?
the one page. There has a band 1 and band 2.
Band 1 and band 2. This one? Data.
Yes.
Yeah.
I'm not sure the band 1 and the band 2. What are the band 1 and band 2, and what's the difference about them, and how to get the band 1 and band 2?
Okay, so I don't explain in detail here. So this is data from WISE survey. It's a infrared survey which contains 4 bands, and it's like an all sky survey here. So band 1 is about 2.4 micron, and band 2 is about 4.6 micron. So it's just one near infrared observation. So, and which is the data I use for this work. Yeah.
Okay, thank you.
Thank you. Oh. So maybe Sof has question.
Okay, so maybe could Lapo go ahead?
Paul or Sof?
Oh, yeah. Yeah,
Please.
okay. Yeah, so if we want to observe the galaxy, but not AGN, other than AGN, there's we using some type to observe it.
Yeah. Use some
方法，
methods, observational method.
Yeah, right. Yeah.
So you mean how to observe galaxies with different observational methods?
Yeah.
So
like using Python and like this one.
This one? You want to share something?
No. It is some method.
Method. You mean how to observe galaxies or how to deal with the data?
Yeah, right. It's different than AGN. If
so, you mean
观察 AGN 以外的星系，对。
Okay, so for non-AGN galaxies, how do we observe them?
Yeah, right. 那个方法、那个套路是不是大概都一样的这样？
So it can be very similar. In fact, AGN are like spatial population in a whole galaxy sample, and they are brighter at some specific wavelengths like X-ray, infrared, or radio. But if we want to observe galaxies, the most used one is by optical or infrared observations. but still people do radio, submillimeter, or other wavelengths, so it's still very similar. So that's not very special in the tools, and we always want to use all the tools to observe both galaxies and AGNs.
Okay, thank you.
Thank you.
Maybe last question is from Lapo.
Yes, thank you. I have a question about the evolution of galaxy shapes.
Yeah.
You showed that galaxies over time get rounder,
Yes.
but I wanted to ask, does this refer especially to especially to elliptical galaxies? I see, because
Yes.
these
So
galaxies are usually flat, and if the method of evolution is mergers, wouldn't we expect that over time disk galaxies form quiescent elliptical galaxies, and so shouldn't we expect a decrease of disk galaxies over time?
yeah. So for this work, we only focus on quiescent galaxies, and if I remember correctly, we just exclude all merging galaxies or other types. So it's possible that if we consider merging galaxies, they can be like a spatial population. But I don't know. It can be a future work to do.
Thank you.
Thank you.
Okay, thank you very much, Yuyen and everyone for asking a lot of questions. So let's thank Yuyen again.
Thank you very much.
Oh, thank you very much. Actually, we have a lot of time for discussion and Q&A at the end of the morning session. Therefore, please ask any questions at that time for both Yuyen and next Toba-san.
Yeah.
And then, sorry, we are running out of time. So, do we want to have a break or
Or should we just continue?